So let's look at the forces on some objects in various situations. Let's start with this. There's a mass in outer space. Good. Just sitting in outer space. What are the forces on that object? Right, nothing. There's not one force. So if I were to draw a free body diagram, it just looks like that. What about on Earth? Gravity. It's just sitting there, same thing, but it's up on Earth. Gravity. What is our equation for the force of gravity on this object? Mass times G, or what's that? 9.8. All right, let's look at Newton's second law. How would we describe this object's motion with Newton's laws? Either one of them. What's going to happen? Yep. Jake. Yeah, keep going. You're right. So using Newton's second law, what's going to happen to that object right there? Okay, it's going to fall. More specifically, what's it going to? It's going to accelerate. That's sort of the vocabulary we want to use, right, for Newton's second law. Why? What's this? What's that? It's an unbalanced force. So it's going to start to accelerate down, right? What does that object want to do? That object wants to stay right there, but it's not going to because of an unbalanced force. So if we were to describe this using Newton's second law, we would say there's an unbalanced force, so it's going to cause it to accelerate. The unbalanced force is the weight of the object, or mass times 9.8, right? Another way to think about this is the Earth pulling the block down. That's going to be helpful to think about later when we talk about pulleys. So that's why I'm going to sort of a weird way to phrase it, but it's going to be helpful later. It's the Earth like reaching in and pulling down on the block. So I have this equals mass times acceleration. This is my force pulling down on it, right? I kind of substituted in right here. I have mass on both sides. Those can just go away, cancel out. Divide both sides by mass. What did I just show? Where have we seen that before? Yeah, what did I just show? Where have we seen this before? We should have seen that a lot, right? When we were doing our motion unit, right? Velocity, acceleration. What was this? When was this the acceleration? What was it called? Free fall. Awesome. So we didn't know why everything fell with an acceleration of 9.8 meters per second squared. We went over to the stairwell. We tested it. We learned that all objects fall with 9.8 meters per second squared. But now we proved it using Newton's second law. So heavier objects, if I have two objects here, right, the heavier object is going to, which one's going to be pulled down towards the Earth more, with the larger force? Or are they the same? Some people are saying same, but then other people are shaking their heads. Which one is being pulled down towards the Earth with the greater force? The bigger one. Right? The weight is how much the Earth is pulling down. I can feel that right now. The Earth's pulling this one down more. How come then they both accelerate at the same rate? What does this one also have more of? Inertia, which means it also wants to do what more? It wants to stay right there. So this one's being pulled down with, this is 100 kilograms, this is 200 grams. This one's being pulled down with a 5 times greater force. Imagine an arrow coming out from this one, pointing down. That's 5 times bigger than the arrow from this one. So this one's getting pulled 5 times more, but it also wants to stay right here when I let go. It has 5 times more resistance to that change in motion. You know what I mean? So it has a force that's telling it to accelerate 5 times more, but then it has 5 times more mass that's resisting that. You know what I mean? So that's why everything can fall to the ground at the same acceleration. We learned that fact earlier in free fall, but we didn't really know why. At least I don't think we did. We just kind of learned it and said, oh, that's cool. I thought heavier objects would have fallen faster. Right? I wasn't in your head, so I don't know. But that's what a lot of people sort of think. It's like, oh, wow, that's weird. Okay, cool. But then we just moved on, right? We didn't really learn why. This is why. Heavier objects have more force, but they also have more inertia, which means they want to stay right there more. All right. This has nothing to do with pulleys yet, but it's going to help us later, some of these concepts. All right. So now let's say we have a pulley system. So we haven't talked about pulleys yet. Here's our pulley system. Everything in red is going to be, let's draw a little chart here. So there's no friction. We'll call this little m and this capital M, just because they're 2 different masses. Thanks. Let's do the same thing. Let's look at what would happen in outer space. If that's sitting in outer space, what would happen? Yeah, everything would stay right where it was. Same thing as here. Okay. What if now I reach and pull this one down? If I reach down and pull that block down. So I put a force on it. Call it just pull. Right? I go and pull on the block. What would my Newton's second law equation look like? I'll write it down. Net force equals ma, right? What's the only force acting on this red? Everything in red I'm going to call my system. I'm not going to call it one object because there are like 2 objects involved, but they're all going to move together. So any group of objects that move together, I just call a system. Right? It wouldn't make sense to call an object because there are 2 of them. So instead of saying like my 2 objects and the string like tied together every single time, I'm just going to call everything that's drawn in red right there my system. So what's the total force on my system? Well, there's only one force because I'm in outer space. There's no gravity, there's no friction here. So what's the net force? It was 0 before, but now what is it? If I add this. If I pull on something, what's going to be my net force? Right, it's going to be this. Whatever this is, yeah. I guess, misleading question. Whatever this pulling force is, my pull force equals mass times acceleration. How much mass am I getting to move? Is it just capital M? Just little m? Or both of them? Both of them. Right, remember if I'm over here, and I'm outer space, and I pull this one down, I could do the same thing. I'm getting, this mass wants to stay here, but I'm pulling it. It has inertia, it wants to stay here, but I'm pulling it. Both of these want to stay where it is. I'm causing both of them to move. So I'm actually moving the whole system. So I have to take into account the mass of the entire system. So my net force equation would look like this. So if I were solving for like, oh, what would my acceleration be? I would just divide both sides by m plus n. And we can think about this. If this is outer space, if this were a car, like really, really, really heavy, would this be harder to pull than if it was just like one of those green carts back there? Yeah, because I'm causing, there's more mass that I'm moving. Right? That would require more force to do the same. Or it would just be harder to pull. It's more resistance to my pull. Okay, what if this was one of the green carts, but this was a car, just this massive thing? Again, it's starting in outer space, so there's no gravity, but I just have a car here, a little mass here, and I pull on the car. Is that going to be harder to move? That's still going to be harder to move. That sort of proves that we need to have both of these masses in the equation. Again, this is going to come in handy when we do the on Earth one. I know these are tricky. This is not the easiest thing to get, but this is the best way I found to explain it. All right, last one. Now we actually finally get to the situation that we're going to be working with tomorrow, which is a pulley system on Earth. So I'll have my same drawing. Draw my system in red, same exact thing. And my hanging mass. All right, so I still have this. Newton's second law always applies, as long as we put the right things in the equation. On Earth, what are going to be the forces in this situation? I'll draw them in brown like I did here. On what? Which object has the force of gravity pulling down on? Or both? Well, all of it does, right? As we're on Earth, so both of them do. So I'll draw both of them. This is the force of little m, so I'll just skip right to the equation. Right, weight is mg. This one has weight on it too, big mg. How come this one doesn't fall through the table? Yeah, what's that something called? What's the force called that balances weight a lot from the surface? Nailed it, normal force. All right. So these two balance, so we don't really have to worry about these. I'll make them dotted. They're still there, but we don't really need to worry about it. All right, so we have our system, and we have, again, this is the Earth pulling down on the block. And again, I word it that way for a reason. This is going to be the exact same situation as this, the outer space where I come in and pull down on it. Now, it's just the Earth coming in and pulling down on this block. All right? So when we fill in this equation, what's the net force on this system? If there's no friction would be pointing that way, but what's the only force that's unbalanced? Riley? This one, right? Little mg. That's the only force, so that's our net force.
Can I go to the bathroom quick?
Yes. How much mass is that little force causing to start to move? All of it, just little m, or just big M? All of it, right. the same as before. So again, solving for acceleration, mg divided by m plus n. So many, this is really hard. So many people, including like mechanical engineers who are adults and all they do is work with physics, get this mistaken. All right? But we're going to know how to do this. What they think is they think the weight of this one is the net force, which it is, but it's only pulling on this. And that's kind of true. As this one goes down, there's tension in the string, and that accelerates it this way. But if it's going to be accelerating this way, the tension isn't the same as this number, because then these two forces would be balanced. And that's not true. So yes, the weight of this object is pulling and causing the net force. But think of the weight of the object as the Earth coming in and pulling it down. So it's not this object going down or pulling down that causes this to move. What I would think of it as the Earth is pulling on this, causing both of them to move. Okay? And that's how we can avoid the mistake. Some people, I'm going to draw this in black and make sure we know that this is not it, think that the acceleration equals mg just divided by m. Okay, the weight of this one is just accelerating this one. Well, it's not. Both of them have to speed up. The pull of the Earth has to overcome this one's inertia and that inertia. Okay? This is a super common misunderstanding. Again, even like mechanical engineers who do this for their real job. One way to prove that it's not this, let's pretend this was like a feather. All right, we don't have a cart attached there anymore. We just have like a teeny tiny mass, just like a feather. Or just the end of the string, like almost no mass at all. So the denominator would be basically 0. What does that mean the acceleration would be? If this was the case. What happens if the denominator is 0? Undefined is what we use in math. I would call it infinite. Right? If we have a numerator that keeps getting bigger and bigger and bigger, or a denominator that keeps getting smaller and smaller and smaller and closer to 0, we get a number that basically approaches infinity. Does that make sense? Does that make sense for the acceleration of this system to be infinite? If I hang this off the side of the table and have a pulley here, even if there's a string at the end, like even if there's no mass attached there, what would be the acceleration of this object? About 9.8. It should, right? Because that's basically like it's just falling. Not infinite. Let's try if we have 0 mass right here. In this equation, the real one, the one that actually works. If we have little mg divided by little m, what are we left with as the acceleration of the object? Just g, 9.8. So that checks out. Right? Thinking about those extremes is a good way to think about, like, especially if we have numerators and denominators. Okay, what happens if this is basically 0? What should we get? Is that what we get? Right? Thinking about those is a good way. And we can do the same thing with, like, little m. If little m is 0, this acceleration should go to 0, because then I have nothing hanging. And it does. If the numerator is 0, we have an acceleration of 0. All right. That was a long way of explaining what happens in this situation. But I think instead of me just skipping straight to that and telling you, and just saying, here's the equation, it's a little bit better, it's a lot better, to try to understand why, especially why we use the whole mass and not just this one as our like F equals ma. Maybe it was overkill, but I think it's worth understanding what's happening. And even if it wasn't, it was good review of Newton's second law the whole way through. After all that, any questions? Okay, this is what we're going to be doing tomorrow. Yes.